If you want to follow along on your computers, this is a tutorial, so it can be a little bit hands-on. These are mostly Marimo notebooks, so if you haven't used Marimo yet, we're using Marimo notebooks, entering 2026, so new notebooks. I've been trying to use them a little bit more recently, mostly to learn them myself, and they work pretty well, so we went with it for this as well. Otherwise, feel free just to follow along. You're welcome to do that as well. Feel free to ask questions throughout. The syllabus, the advertisement claimed that no prior knowledge was expected about Bayesian inference or BART or pymc. So any clarification that's required, do not be shy about asking. You're probably not the only one that has the question if it helps you understand better. So please do interrupt. So yeah, I'll do a little bit of intro, a little bit about the BART algorithm, a little pymc intro for those of you who have not used the package before jumping into the notebooks that use BART within pymc. So hopefully everybody's got that URL, everybody's able to clone things. Oh, and environment-wise, it's a Pixie setup. It's very easy if you haven't used Pixie before. Really easy. It all installs into your home directory. You don't have to touch the system at all. So just follow those instructions if you'd like to. And then when it comes time to run the notebooks, it's Pixie run Marimo edit, which is a little awkward. Or you can just do Pixie run tutorial and it will pop up a little dashboard that's not unlike the Jupyter dashboard that you might be used to. Okay. Yes, sir. Could we get the repo? The repo, yes. It is github.com/my last name, Pydata _Bart, London _Bart. Now I'm going to switch to slides. Cool? Okay, so I want to tell you a little bit about what BART is. A lot of folks probably come from machine learning, where we know about CART, classification and regression trees. This is a very similar, analogous, Bayesianized version of that, I guess you'd call it. So I just wanted to start by gently introducing you to the topic before diving into the software, because pymc's kind of mission is to abstract away a lot of the detail and make it a very high-level implementation, and so you kind of miss all the fun doing things that way. So I always like to do things, kind of by hand first, or at least give you a little peek under the hood. So I'll start with what is likely a familiar model to you, which is gradient boosting, right? We've probably seen gradient boosting before. This is a classical machine learning algorithm where you've got essentially an ensemble of what they call weak learners, so really small decision trees, and they piggyback on one another by fitting subsequent trees on the residuals from all of the previous trees, right? And it's nice, it's very fast, non-parametric. You get a little wiggly line here. This isn't a particularly good fit, but this sort of what you'll see. This one's a slightly overfit, I suppose, and that's also a trait of gradient boosting, unless you're careful about what you're doing. But it's a fast, fairly accurate point predictor. But one of the drawbacks is, you just get one curve. You kind of massage the curve until you get it the way you want it to, and you've got your kind of one optimal function that you've just fit. So no uncertainty, and it's sort of equally committed across the entire range of the data, whether it's dense or sparse or what have you. With BART, it's the same sort of sum of trees structure, but it's got a full posterior distribution. Sorry, this is much easier to see on my screen, but little blue lines on the outside is a little prediction or a credible, what they call a credible interval. It's a probability interval that describes how certain you are about your estimate at each point. And the band will widen where the data is sparse, more uncertainty, and it'll narrow where the data is dense. So you get calibrated, relatively calibrated uncertainty. That's kind of what we're building towards here. So structurally, it's like gradient boosting. Again, we're summing trees like we were before, but we're not doing it in kind of the same sort of greedy snapping up the residuals sort of way. It's going to be a slightly different algorithm. It's going to be using backfitting, posterior backfitting. And then importantly, it's Bayesian. So you get everything that's output from it is in terms of probabilities. So you don't get a point estimate, you get a full probability distribution to describe the uncertainty. And then also, as a means for avoiding overfitting, we can use prior distributions, which I'll describe in a bit, to essentially regularize things, constrain essentially the range of values to try to avoid overfitting. So that you don't have to go through and do, kind of pruning and other sorts of exercises that you'd have to do with gradient boosting or things like random forests. So again, no prior Bayesian experience required, but this isn't going to be a university course. I'm just going to kind of give you a little primer here. You got to show Bayes formula, right? So here it is. So with Bayesian inference, the idea is that everything has a probability distribution around it, right? So everything that is seen or unseen that is relevant to your problem. So unknown parameters that you're trying to estimate, the data that you observe, data that you haven't observed yet, predictions, imputed values, they all have probability distributions. And the idea is that you describe them with probability distributions, and then you use information from the data in the form of a likelihood function, and you update them to a posterior distribution. So here theta is a vector of parameters. It's all the parameters of your model. D is the data. And so prior is kind of what we know about the world before we see our data, and then the posterior is what we know afterwards. And then again, we start with probabilities, we end with probabilities. And the reason that we're able to do that is because of this normalizing function, which is known as the evidence or the marginal likelihood. And that's kind of the sticking point for Bayes. That's what makes it hard, because that's an integral. That's essentially the numerator integrated over all of theta. And when theta is when it's a vector, it's impossible to do kind of enclosed form. So, one of the simplest models is just the normal distribution, right? You're trying to estimate some, let's say some normal mean. You got some data, y, that you're saying is normally distributed with some mean and standard deviation. Well, what you do is you put a prior on mu, and so we'll just give it another normal distribution. And we'll set it with some hyperparameters. And then we'll put a prior on sigma, or sigma squared, and we'll use an inverse chi-squared. And there's all these choices you have to make about priors, how to choose priors. That's a whole thing. But irrespective of what you choose, you plug those in as a prior, you incorporate a likelihood, and then you kind of turn the Bayesian crank, and you turn that into a prior distribution, and you learn from your data. And in the case of a normal like we just had, it actually is closed form. This is one of the few, it's what's called conjugate, and you can actually do this in closed form. And you can actually see that the posterior mean is actually a weighted average of the prior and the data information, which is quite nice, right? That's what you expect. And so if your prior is really weak, the data will dominate. And if your data is really sparse, you don't have much data, but say you have prior information, maybe it's a topic that we've done a lot of research about, then the prior will dominate. So you got to be aware of those things. But again, most of the time, except for toy problems, you can't do Bayesian inference without computational help. It's impossible to integrate it in closed form. It's impossible to sample from it in using, well, you can't sample directly from the posterior distribution most of the time. So what we got to do is we use algorithms like Markov chain Monte Carlo. And Markov chain Monte Carlo, what it does is it says, oh, I can't sample from my posterior distribution, but I'll use this auxiliary distribution to sample candidate values, and then the algorithm will decide whether that proposed value is good or not. And you do this iteratively, and it's based on this acceptance probability. So you'll propose a new value, theta prime, and you'll accept it in proportion to kind of the ratio of the posterior distribution under the new value over the old value. And this is known as the Metropolis-Hastings algorithm. It's a flavor of Markov chain Monte Carlo. And so you get, stuff like this. So this is Metropolis-Hastings in 7 lines of Python code. So you get this sequence of samples, and if things go well, it looks like a fuzzy caterpillar, right? It's not trending, it's kind of homoscedastic, so it's not, the variance is kind of the same. And so this is estimating a beta distribution, right? Some unknown beta distribution. And voila, we have a beta 3,2, and that's what it looks like. Okay? That's the idea. And there's lots of, Metropolis-Hastings actually isn't a very good algorithm. It's just the easiest one to teach, so we see it all the time. Yes?
So the point is that blue lines are these values that you sample
yep.
the MCMC, and then you can reconstruct the beta from that.
Yeah, exactly. So, yeah, thanks for clarifying that. So what are these samples? These samples are sequential draws from a Markov chain that, through theoretical guarantees, is indistinguishable from the true posterior distribution. So this is a time series of the samples as they were drawn, and then this is just a histogram. So those are the same values. And that it's just notice this is centered around kind of 0.6, and so is this. So it's just the same data. So so the output from Bayes is not just a single point, nor is it, a confidence interval. It's a whole distribution. And so once you have that, you can do anything you want. You can, I want the median, I want the upper 90th quartile or percentile, anything you want. So once you're able to do this, everything else kind of comes for free. You can make predictions. It's really, really nice. But it just requires a lot of work not a lot of work, but a lot of computing to get this. Okay, so that's Bayes and MCMC. Any clarifications? Seriously, like anything? Yes.
Almost a side question in a way. So one of the benefits of the fact that you're not just getting the point, you're getting a distribution, is you could also then use that to perhaps kind of understand, clearly you now understand the distribution of the data.
Mm-hmm.
So now you've deployed your model out there in the wild, and you want to sort of understand, say, model drift.
Yeah.
As a result of data itself changing.
Yep.
I don't know if you just want to elaborate very briefly on how.
Yeah. So this isn't data, right? This is uncertainty about what the true value of some parameter is, and a beta distribution describes usually probabilities. Notice it's between 0 and 1. So some rate, for example. And the thing about Bayes, the thing that makes it different from the stats that we probably learned in school, frequentist classical stats, is that parameters have distributions. And it's not that we think that it's random, but it's an epistemic thing. It's a state of knowledge. We just use probability distributions to describe our uncertainty. And so, this is based on, some amount of data. You can go out and collect some more data, or say the data's streaming. You can run another Bayesian update here, right? You could use this as the prior for the next set of data. And then that data, might make this shrink down. And if you had, millions of observations, whatever this X value truly is, it'll collapse onto kind of a point probability of 1. So it's the state of information. As n goes to infinity, it collapses to the true value. Yeah. Cool. Yeah, good question. We want, again, we're going to abstract away all of this. We don't really have to know all this. I'd just like you to understand a little bit about what you're seeing before we dive in. Okay, so back to trees. So, for those of you, again, unfamiliar with maybe regression trees, this is really all it is. It's a non-parametric statistical method that simply takes a parameter space and subdivides it. And so for a particular point, you simply follow the diagram. So whether you're above or below 0.5, if you're above 0.5, then you see what the value of x1 is, and if it's less than 0.3, you end up with a value of 0.9. And so each of those red boxes is what's called a leaf node, and that's the output from a tree. So there's no parameters. It is just what we call a piecewise constant function. And the parameters really are just the cut points. It's where we decide to make these cuts. And the number of cuts scales with the data. And that's really what non-parametric statistics is. It's not no parameters. Statisticians are just really bad at naming things. It's that the number of parameters grows and shrinks with your data. So things like Gaussian processes. I was here last year, I taught a Gaussian processes one. That was also non-parametric, but this is very different. And so the mean, essentially, of y is inside of each leaf. So we got this piecewise constant function. So this would be a single tree, right? Single tree, and based on different subdivisions of x here. And it's starting to follow kind of the true f. And the more you slice and dice it, the closer you'll be able to fit the data. But then, of course, you get to the point where you subdivide it so much that you can fit every single point, but then it becomes overfit, right? You won't be able to predict out of sample. Like this line will predict out of sample quite nicely, but if we try to add a more complex tree, the point is not usually to fit to the data in hand. It's to predict future data or data that's not in your data set. But we don't just use one of those trees. Irrespective of which algorithm we're going to use, they tend to be highly biased. So what we do is we want to sum them. So we'll have one tree that's fit to the data a particular way, a second tree that's fit to the residuals of that, and then what we'll do is we'll add them together. And you can see that it's already starting to look like the target function. And so we'll do that over and over again. We'll make a third tree that's fit to the residuals of the sum of the previous two, and we'll add that as well, and so on. So we repeat until essentially the residuals are noise. So the residuals it's not changing, essentially. And then BART just, additive boosting does that too. BART just makes it Bayesian. Right? And so this is the idea. So we're adding up to 100 trees here, and as you can see, as it hits 100, we get something that pretty closely approximates the true function. And the idea is that these are several shallow trees. They tend not to be trees with 4, 5, 6 branches. It tends to be 2 or 3, maybe 4. And we're going to use prior distributions to constrain that. In other algorithms, you'll do things like pruning, or you'll set a fixed maximum number of splits. So yeah, what we would do in machine learning algorithm is we'd use cross-validation, right, to kind of fix the hyperparameters. But cross-validation is a drag, right? It takes a lot of computing. You've got to fit to lots of different subsets of data. We're going to take a different approach, and we're going to put a prior distribution on depth. What does that mean? Well, what we do as Bayesians, when you don't know what something is, what the value of a hyperparameter is, what you do is you put a prior on it, add it to the model, and estimate it, and that's what we're going to do here. And so what this will do is it will allow it to be flexible. It will constrain it to be 2, 3, 4, but if the data demands it, Remember I said how Bayes' formula is just the compromise between the prior and the likelihood? Sometimes the likelihood will overwhelm that prior and it will allow it to exceed 2, 3, 4 splits. But the data has to be convincing, right? And then, yeah, leaf values, additional, what we call shrinkage here, so it regresses them back towards 0 unless the data demands that it be otherwise. And then a noise parameter. So there's really 3 types of parameters: the shape of the tree, the values of the leaf outputs, and then the noise, which is everything else, because in the end we're going to be doing regression in a minute. Okay, so yeah, here's the prior on shape. So from the original BART paper, Chipman et al., this is the prior distribution that's used on the number of trees. It's a discrete random variable, and it's got 2 parameters, alpha and beta, and you almost always just choose these 2 values. You can choose anything you want as long as they're 0.95 and 2. I mean, you can choose other things, but that you typically, because this is what we want shallow trees, mostly 2s and 3s, sometimes 4s, rarely more than that. But you can, go as far as you like if the data demands it. So you're not doing yourself any favors doing this. That's probably not too bad, but again, sort of the tried and true setup is that one. It's very rare that you kind of give 2 specific values for a prior in Bayesian inference, but in this case, it works most of the time. But they can always be overridden. And so this is what you get. So we get every iteration of MCMC, you'll get a new set of trees. So I showed you a set of 100 trees that did a pretty good job of estimating that function. This is what you'd start with. And then what's going to happen eventually is we're going to grow these trees. So let's see what Metropolis Hastings looks like on tree structure. So typically Metropolis Hastings, you're in typical stats, you're like a standard regression model, you are dealing with continuous parameters. You sample from a normal distribution, propose a new value, and update it that way. But what we're doing here is we're sampling trees rather than continuous or even discrete values. And so our moves here are either going to be to grow a tree, so you'll propose adding a split on one of the values, on one of the leaf nodes, turning it into a split node, or we'll prune it, we'll go the other way, we'll make it smaller. And then we do that same acceptance rejection Metropolis Hastings step. So you'll propose something, you'll like it or it won't, and then you go from there iteratively. So some of them will start growing, some of them will prune back, and you'll get, and the idea is to kind of cover all of the uncertainty about the true underlying function. And we're not relying on any one tree to describe the whole thing. Again, it's the sum. Our target is the sum, not an individual tree.
So if I get it right, compared to how we grow trees in like regular machine
Boosting,
learning,
yeah.
The way this changes is that we adopt MCMC, and instead of drawing from a candidate distribution, we draw trees from a distribution of trees.
Yeah, or we draw, exactly. Yeah, there's a population of trees, a notional population, and you're drawing from them. Here we're doing it from these little steps of, so you can't go from this tree to a tree with, 5 branches directly. So they're very small steps. This actually isn't, so this Metropolis algorithm isn't the one that pymc-bart currently uses because it's not very efficient. It uses kind of a particle sampling approach where a whole tree is proposed, and it could be way bigger or way smaller. So it's a little bit more flexible. But in this case, the thing that's being proposed is just a slightly larger or a slightly smaller tree. So they can get big, but they've got to do it stepwise.
So you don't propose the whole tree, but the next iteration on the tree that you grow.
You are proposing a whole tree, but it's the difference between the two that determines whether or not it gets accepted or not. Yeah.
Well, you're proposing different trees, and then the algorithm picks up the better one given the previous one.
Sometimes it picks the better. So that acceptance ratio you'll notice that it's a probability. Well, it's more than a probability. It can be it has to be positive. So it's a ratio, and if it's greater, if the proposed value has a higher probability than the current, it'll be greater than 1, and you accept it all the time because you kind of flip a coin. If it's less, then it's accepted in proportion to how good it is. So if it's half as probable as the current value, you'll have a 50% chance of accepting it. If it's 1/100th of the probability, you have a 1 in 100 chance of accepting it. So the idea is not to kind of go to a mode of some kind. You actually want to characterize the whole distribution. And so sometimes you'll take a jump out into a big tree or a really small tree. Most of the time it'll be in here. So the MCMC is just the algorithm is a way of characterizing the entire distribution, and that's just kind of one of the. It's not every Markov chain that allows you to do MCMC. It has to have specific properties, and that kind of acceptance rule is one of the things that gives it that property.
And how do you sample? How do you like regular trees that go like follow these criteria, such as I don't know, like the R-square ratio, whatever, between the subfields that it creates? How does this algorithm pick the feature that it wants to split on?
Oh, it proposes that as well. So this is what the proposal is. So this is a proposal, and it involves picking a split.
A generic, like whatever.
And they'll have rules. Yeah, they'll have rules depending on if x is a continuous variable, or it could be a binary variable, could be a categorical variable. So we have different split rules. Yeah.
Okay.
Good question. We'll get to it in a minute too. Yep. Yeah, so this is what the acceptance ratio looks like for trees. So it's our likelihood, our prior, and then whichever move that we've just proposed. And that's the logarithm on the log scale, the log acceptance rate. So 3 pieces. One is kind of how much better the data fits, which is the first term. How the prior kind of feels about the new shape in the second term, and then just kind of proposal bookkeeping. The criterion is called the detailed balance equation. It's got to satisfy detailed balance in order to guarantee that we'll converge to the true posterior. And so having this particular form of the acceptance rate guarantees that. So yeah, in practice, this kind of stalls on really big trees, and so we move away from Metropolis Hastings. In general, Metropolis Hastings isn't a very good algorithm. It's just really easy to teach. And then the other parameter is the noise. So this is essentially what's left over after you've added all your trees together. And that's got to be a prior as well. And this is a nice metric on, you kind of observe how sigma changes as you fit more trees. And at some point it'll plateau, right? There's only so much juice you can squeeze out of the lemon. And you can use that as a check on whether or not you're done or not, in terms of the size of the model, how many trees you want to fit. So yeah, putting together then, this is backfitting. So what we're fitting to is we take the sum of the data, and you subtract out the current set of fitted trees. And that's essentially what the target is. And so we sample a new structure. So we're going to either grow or prune our trees. We're going to sample for leaf values. So the output of each leaf comes from a distribution. And then finally, that noise parameter. And this is what's known as Gibbs sampling. It's a special form of Metropolis Hastings where it allows us to sample one parameter at a time, not all of them at once. So first you're sampling structure, then you're sampling leaf, then you're sampling noise. Actually, it doesn't matter which order you do them in. They just all have to be done in one pass. So this is one pass of kind of a Gibbs sampling approach. And so it ends up looking like this. You specify M trees at the outset, and then you let them evolve based on acceptance rejection. Like this step here, there was well, I guess that's 3 to B, but this one ended up in the same size that it was at step 3. This one grew, that one shrunk at that step. And then we typically have a number of what we call burn-in or tuning iterations, where we actually discard our sample because the algorithm is still tuning itself, and the samples are not going to be reliable. So we'll take, B iterations, but we'll discard L of them and keep the rest for inference. So that's kind of what it looks like in code. So it's, again, relatively easy to implement. So again, what you get here is a whole set of trees. So each blue line here, each blue skinny line is a posterior draw. The fat line is the mean of all of those, or the median, mean. And again, you can get whatever percentiles that you need. So this is kind of the Bayesian payoff, really. There's no cross-validation grid. There's just priors that the data can override. Oops. Didn't mean to do that. Okay. And then, choice of M. So more trees tends to be better, but again, no free lunch in machine learning, right? There's a trade-off. There's a computational trade-off. So you can see that, so 5 trees here, you end up with a large, so the x-axis here is sigma, so this is the noise parameter. So whatever the tree can't describe goes into the noise term, right? So you want to make that smaller, but you can see after a while, there's no real difference between 20 and 40, really, maybe a little bit. And this is from a toy simulated example. That's the true noise parameter. So, it's typically, for applied problems, every time you see a presentation on BART, everybody's got their favorite value, and it typically depends on what field you're using these in. Some people use 200, some people use 50, and everything in between. But somewhere between 50 and 200 is where most people play. And then the nice thing, too, is that longer sampling doesn't cost you anything. A lot of times with boosting, if you keep sampling, it'll, particularly the training error will, it'll just overfit, right? The same is not true for BART. You can keep sampling with it. It doesn't matter. You're just doing more MCMC sampling in this case. Okay. Cool. Any questions there before we dive into some notebooks? Yeah.
So I think what you indicated is that longer sampling doesn't really have any major impact in overfitting, which obviously is kind of contrary when you're looking at conventional
Yeah.
machine learning models. So I guess then in this particular case, there's no need to have an early stop strategy of any sort.
Nope.
Because you can have as many. Is that correct? You can have as many.
Yep. Yeah. It's using the probability. It's using the posterior probability, which is regularized by the priors, right? So if you have weak priors, it will sometimes start making the trees really, really large. And large trees is what ends up with overfitting. Because if you think about a branch in a tree, when you add trees together, what you're really describing is an interaction between variables. And it's common for most problems to have 1, 2, 3-way interactions. You rarely have 5-way interactions, 7-way interactions. That's just noise, and you're fitting to noise. So, and priors is what we use to regularize that away. All right, let me get the notebooks up here. I might have to change the configuration of my screen here. Let me do that. Hold on. Let me just go into my display settings here and mirror my screen. Mirror. Apply. Hooray. All right. Okay. Wow, this is really large. Okay. Where are we? 2? That's pretty good. Okay. So a quick introduction to pymc. I wonder if I can make this a little bit smaller. That's really big. About. That's more like it. That's better. Everybody cool with that? All right. So yeah, just a little introduction to pymc syntax before we dive in. So pymc is just a implementation of a set of fitting algorithms for Bayesian models. It allows you to specify models at a high level and fit them using Markov chain Monte Carlo, variational inference, a lot of different algorithms. We'll focus on, we're going to focus on pymc-bart here, but the examples here, the approach is the same no matter what you're using. And it separates those two concerns. A model that's specified, a model that's being fit using MCMC and one being fit using variational inference, the model looks the same. So it's kind of a separation of concerns. And so I'm going to talk here about how models are specified. So we instantiate a model object. So we imported pymc as PM. And so we create an instance of a model. And what we do is we kind of co-opted the with statement here, the context manager. And if we declare a variable inside that context manager, it automatically gets added to the model. And what the model does is it builds what's called a directed acyclic graph. So it constructs the dependencies between the variables. So here, all I've done, simplest possible model, just essentially a prior distribution. A normal, this is saying we have a normal called Z or Z, and it's got a mean of 0 and a sigma of 5. And so our model just has kind of one element. And our model has, attributes, so a set of named variables, and you can see that it knows that it's got a normal distribution with particular parameters. And the model gets compiled, so there's a backend called PyTensor that allows us to use different backends like JAX and Numba to run the models in efficiently. So we compile it to whichever backend that we happen to be on. And once we compile it, we can pass it values, calculate log probabilities. That's the main thing that these distributions do. Because remember that accept reject step, it's all based on the probability of the model at particular values. Well, this is the probability of the model if we say Z is 2.5. So there's really two core components. There's actually three, but the third is very esoteric. It's really divided into things we've observed or can observe or have observed and things that are unobserved. Things that are unobserved, stochastic random variable, right? It's something we're trying to estimate. So we put a distribution around it to encapsulate what we know about it, the state of knowledge. So prior distributions. Likelihoods are also stochastic, but they're kind of pinned to a particular value because we kind of attach our data to it. So data also has a distribution. So saying that X is normally distributed, that's a stochastic random variable. Deterministic variable is just a transformation of existing variables. We've taken X, we've multiplied it by beta and added mu. We haven't added any additional uncertainty here, so it's a deterministic. And that's really it. With different forms of both of those, we can build almost any model. Distributions and deterministics have shapes, so they can be scalar, they can be vector valued, they can be matrices. Everything underneath is a tensor. So PyTensor used to be the Theano project back in the day, is just a way of dealing with tensors. And the nice thing is in pymc you can give our tensors named coordinates. So let's say we're modeling something about 5 cities in Canada. So we have a normal distribution and we want it to be length 5, but we don't just want to say shape equals 5. You can just say shape equals 5, but it's way cooler to pass it the list of cities, because then when you go to plot, all the crazy posterior distributions, it'll have Vancouver on it instead of x1 or whatever, x0. Okay, so kind of looks like that. So that's a multivariate. Well, it's not a multivariate normal, but it's a vector valued normal distribution. And then you can, in addition to calculating log probabilities, you can draw samples. So here's 5 draws from a normal distribution of size 5, so it's a 5 by 5. Okay, so you can arbitrarily calculate log probabilities and generate random numbers. So just a quick example of a model in pymc. This is kind of an unpleasant example. It's a rat poisoning example. So there's 4 doses of rat poison of some kind, some nasty substance. Each group has 5 rats, and then these are the numbers that die in each. And we're trying to calculate the toxicity of whatever this nasty substance is. And so what we do in this case is we build a logistic regression. So this is a logistic regression model. Y is the number of deaths, and we say that that's a binomial distribution, right? It's a binomial draws, sums of coin flips, essentially. Live, die, yes, no, male, female, that kind of thing. And the quantity of interest is P, the probability of death here, and we're going to make that a linear function of the dose. So this is a logit linear model, linear regression model. And so how do we do this or write this in pymc? Nice thing about pymc is that really every line of math that you'd write on a whiteboard, you typically have 1 line of code in Python. And so you really have to ask a couple of questions. What are our unknown parameters? Well, if we look at here, the only 2 unknowns here are beta naught and beta 1. Everything else is just transformations of those. And then what's the distribution for that we should use to characterize our beliefs about their values? Well, in this case, it's a linear regression model, so we'll just use normal distributions. There are a lot of different choices you could choose, but it looks like I'm using log normal for 1 because it's toxic substance, so we don't ever expect fewer deaths with a higher dose. So log normal will constrain it to be positive. That's why we chose that. So we put a normal prior on beta naught, log normal on beta 1. This is a deterministic transformation of those, so that's the inverse logit function. LD50 is the lethal dose 50, which is the dose at which 50% of the population would be expected to die. And then the binomial is the likelihood. And it's a likelihood because it's been observed. So this is where you pass the data, the number of deaths. That's it. There's really no notation for likelihoods and priors, right? It's just based on one having data associated with it and the other not. So it's just because a binomial could be used for a prior somewhere and a normal could be used for a likelihood somewhere. It all depends on whether you have data for it. And so this is the directed acyclic graph that's drawn. That's the model. And so Bayesian inference reasons over this graph. It tries to estimate the things at the top, the unknown quantities. Okay? And then this is what Thomas Vicky calls the magic inference button, which is pm.sample. There's a lot of complexity hidden away here. The only argument I'm passing it is a random seed. And we've got pretty good default default argument values for what most people do most of the time. But there's a whole bunch of optional parameters. So how many draws you want, by default 1,000. How much tuning you want to do, by default 1,000. How many chains. So you can run these MCMC algorithms in chains. They're embarrassingly parallel. You can just instantiate a whole bunch of them. You should do more than one. How many cores you want to use, etc. Okay, so a lot of complexity hidden under there. And then it returns as of a couple weeks ago. So we've had major updates to all the pymc ecosystem packages. pymc is up to version 6 now. RVs, and there'll be a talk about RVs by Oriel later on that I think it's right after this one. And so Oriel's package, RVs, provides all of the diagnostic tools and the data structures for holding all of the MCMC output. That's another issue, is that it involves managing all of these samples. And so it's based on Xarray now, and it allows us to have, elements of different sizes, and they're all labeled and really nice to use. So we get all of our posterior draws in here for each of the values of beta naught and beta 1 and the LD50, as well as sampling metadata. And so you get the plot kind of like we saw before with that beta distribution. So there were 4 chains sampled. Each one has a different line type, and you can see they all kind of do the same thing. So that's a good sign. It means they've converged to kind of the same thing. If they're all over the place, that means, you know, we're not done yet. We've got fuzzy caterpillars. We like fuzzy caterpillars. We don't want them to kind of be wandering around, random walking. We don't want them to be, you know, cone of uncertainty. We want nice, evenly sort of random samples around the mean. Cool. And then you can sample from the posterior distribution. So once you have, the nice thing about a Bayesian model is that it becomes a data simulator once it's fit. So I can sample experiments. So these are, so the black points are the actual observed deaths, and each blue line is a potential kind of true underlying function. Right? So that's kind of the uncertainty around the functional response of unfortunate rats to nasty substance. And you can see that the black dots are, you know, well within the probability mass here. And then the last thing before we move on to BART stuff is, and this is what we used to generate those lines, is that once you have this data, you can pass in now other inputs to try to get predictions. This is called the posterior predictive distribution. So we'll put in, you know, a bunch of different doses and set the data. So we actually have data objects in our model. And if we add the data to our model as nodes, we can swap in new values, you know, test data for training data, and so on. And so there is a set data function where you can add, let's say, the LD50 value that we estimated, the mean of that, and we can calculate, you know, the expected number of deaths at LD50. And there it is. That's the posterior predictive distribution, and it's kind of peaked kind of in the middle. Okay? Whew. All right.
Sorry,
Yes?
what was the point of the posterior predictive distribution? So
It's to, well, it can be used for model validation. So you generate sample data from your model. And one way of doing model validation is to say, all right, if this model is a good representation of the data generating mechanism, then samples from sampled data sets from this model should look like the data that was used to fit that model. And that's what you saw with those blue lines. And so you say, could the data have come from this? And if the data is over here and your model is sampling over here, there's something wrong. But in general, it can just be used for prediction. So I've fit my model. Now I want to predict on, you know, next year's data or the next experiment, that kind of thing.
Thank you.
It can be used for imputation as well. Okay, on to BART. So let's talk about BART for regression. I like to use different data sets every time. I was just at the F1 in Montreal week before last, so I thought, hey, there's got to be a bunch of F1 data, and there is. And there's a Python interface to get it. So what we're going to try to do is use BART to sample or to estimate lap times for Formula One cars, because there's a lot of variables that are available. So I'm just taking 5 races here because we want these models to run in a reasonable amount of time. So there's variables like the conditions, dry, hot, wet, venue, driver, tire type, whether it's hard, soft, or medium, a bunch of input variables. It's not super important which. And so we want to try to predict, you know, who can get fast lap times. This is a Marimo notebook, by the way, if you haven't seen them before. If you hit this button in the bottom right corner, it will run all the stale cells. It will automatically initiate itself and start running when you open it up. And the big difference between Jupyter and Marimo is that dependencies between cells are automatically kept up to date. So if you make a change to a parent cell, everything that depends on the value of that cell will automatically get updated. So you don't get that stale cell syndrome that you sometimes get in Jupyter. So yeah, here's the data. So tire compound, spelled tire with a Y in Britain, so it's T-Y-R-E. Which lap number, position, air temperature, all of these things. And so this is typically why, a lot of the reason we use BART is that we have a lot of variables. They may interact in ways that are hard to pre-specify, right? Typically when you do a linear regression model, you've got to pre-specify all your interactions, right? You got to say this interacts with that, but not this. And there's a three-way interaction over here and blah, blah, blah. And that's great if you know a lot about your system and you know, the things that you want to estimate and you understand it really well. But when you've got, kind of the machine learning approach is you've got hundreds of columns or dozens of columns or whatever, and you're not sure how they're going to interact and they're potentially nonlinear, that's when you want to use BART. And depending on what computer you've got, I've got my little Ryzen framework here that's not super powerful. You all have your M2s and M3s and stuff, so you can probably crank it up to the full data set. So it can let you choose there. And then, so we got our data, and then a few things that we're going to have to specify is splitting rules. So remember, one of the things that BART is going to do is it's going to split variables, and that's going to be a proposal. It's going to be, split on a particular variable. If it's to the left of it, you get one leaf. To the right, it's another. Well, how do you split on that? And it will depend on the type of variable that you've got. So things like tire type, hard, intermediate, soft, we're going to use a one-hot encoding. So you're just going to sample from one of the three values. There's a subset split rule if you've got ordinal variables, for example. There's continuous split rules and so forth. pymc-bart will make a reasonable choice for you, but you can override them if you want. If you prefer one hot to subset split, for example, you can override them. And then I'm doing a random 80-20 split for testing and training. Typically in Bayes, we don't have to do that. We can actually approximate, leave one out, cross-validation using the MCMC samples, which is really nice. You don't have to throw out, or not throw out, but keep a subset of the data away from the fitting subset, so you'll have improved precision. And so let's see what a model looks like in pymc-bart. So we've imported pymc-bart as PMB, and just like another, so it's really just another variable, like a normal distribution or a binomial distribution, except it's called pymc-bart. You give it a name, so all the variables in pymc have a name. X, the inputs, Y, the outputs, M, the number of trees. Those are, I believe, the only required arguments. Everything else has potential defaults that we can look at. All right. And then the other, some of the other hyperparameters we'll just use standard pymc variables like normals and half normals on the residual standard deviation. So this is what it looks like here. So I have a set of splitting rules, and there's going to be one for each input variable in our input data set. So I've got a certain number of continuous split rules, and then a one hot and a subset split. And you just got to make sure that they line up with what you've got in your data set. And then here's our with pm.model. Again, we can use our labeled dimensions, so which observation and which variable that we're dealing with, so that again our output will be properly labeled. And we're passing our data in as this data object so that we can again replace it with test data set, a test data set later on. And then here's the punchline here. pm.bart. It's rather unusual that you pass y to a random variable, but this is what it kind of uses to initialize the model, because it's going to initialize it at the data means. So we pass it y. You typically don't pass it to other random variables. And then we're going to use 100 trees here and pass it our split rules. And then we've got to put a prior around the residual noise. So remember, you've got the sum of trees that explains, hopefully, most of the variability, and then the residual. In this case, we'll have a half normal. The reason we use a half normal is because standard deviations, variances have to be positive, right? So a half normal is just a normal that's cut at zero, centered at 0, and the positive half is kept. So it constrains it away from being negative. You don't have to do that. You're not doing yourself any favors if you allow it to be negative. It won't break. It just might not run as efficiently. I think I used inverse chi-squared earlier on. There's a whole bunch. So again, prior choice is a whole topic unto itself, but there's a lot of canonical choices, and half normals for standard deviations is pretty standard. And then our likelihood here is a normal distribution. So we're going to say that lap times is normal. And you might say, oh, why isn't it log normal? Because you can have negative times. Even if you're Max Verstappen, you're not having negative times around the lap. So, but the times are so far away from 0 that in this case, it doesn't really matter. And normal's just easier to deal with. And then we do our magical pm.sample, just with the defaults. And so again, by default, it runs 1,000 iterations of tuning, 1,000 iterations for inference, and so you get 2,000 in each chain. So you actually end up with 4,000 iterations because there's 4 chains going on. So you could do 16 chains, and if you only needed 1,000 iterations, you only need to run this for a few dozen times. So you can subdivide it that way if you want. And then you get some nice feedback here. We're pretty good about reporting useful diagnostics to you. You can see that it tells you so a step function in pymc is the type of MCMC algorithm that you're using. And it's really just a function that knows how to take one step of a particular MCMC algorithm. And so most of the time it uses what's called a nuts algorithm. If you're just running a regular regression model, the nuts algorithm is a really efficient gradient-based method for doing MCMC, really, really good. The problem is it's gradient-based, and guess what? Trees, you can't calculate gradients on trees because they're discrete, right? So you've got to use pg-bart, which is particle Gibbs-Bart sampling. And this is one, it's not the same as what I described before. It's a more complicated algorithm that uses sequential Monte Carlo. But it's faster and better than Metropolis Hastings. So the nice thing is it picks, so one of the things that sample does for you is it chooses usually the best algorithm for that variable. And it will choose different algorithms for different variables depending on whether they're continuous or discrete or whether they're trees or not or what have you. So it's just reporting what it used so that if it makes a mistake, you want to override it, you can. It tells you what it did, how long it took, and then it gives you diagnostics. It says that our hat statistic is larger than 1.01. This indicates problems during sampling, okay? And then the effective sample size per chain is smaller than 100 for some parameters. So effective sample size, when we're doing MCMC sampling, it's not independent sampling, it's dependent sampling. It's a Markov chain. And so your effective sample size is always going to be smaller than the number that you actually took. Right? They're not independent draws, they're dependent on the one before. And sometimes they're heavily dependent. They've got big lags to them. And that's what's happening here. And so we can go back and tune this a little bit later on. But you can see that it's doing not a terrible job predicting laps. So these are posterior, so these are their estimated lap time, and then here are the observed. And you're getting the intervals on each of them, and a lot of those intervals are intersecting, the line. So the dotted red line, which is perfect correspondence. And then here's the thing that we want to monitor, which is the residual standard deviation. So if we went to 150 trees, hopefully that SD posterior will go closer towards 0. The RV's team wrote a really nice paper on model diagnostics for Bayesian inference, Aki, Vetteri et al. And they sort of set minimums for some of the diagnostics. So effective sample size, you want to have at least 400 for kind of reliable inference for the posterior distribution. You can see that for both the tails and the bulk of the posterior distribution will have kind of different properties when it comes to effective sample size. You can see they're both, even though we had warnings up here, they're still pretty clear of the kind of minimum, right? And all you have to do if you want a larger effective sample size, well, the best way is to fix the problem with your model, but the other way is just to keep sampling, just sample more, and you'll get more higher effective sample size. And then R hat is a measure of mixing. So an estimate of whether or not your model's converged or not. And you want them to be really, really close to 1, really, really close to 1, like less than 1.01. When I first started doing Bayes, the cutoff was like 1.1, and then it was shifted to, no, it has to be 1.05. And now it's 1.01, so it keeps getting closer to 1. It's making our lives more difficult. But you really want it to be all on this side of the line, and you're seeing that we're still getting some that are larger. Not always a deal breaker, particularly with models with lots of parameters. So this isn't terrible. It's not ideal. It's realistic. This is what you get with real data sets. But there are things we can do. We can improve it. This is the first shot of the model with default arguments. This is pretty good. Okay, and then having fit the model, we can take our holdout set. No, that's not the holdout set. That's the training set. Oh, I'm doing posterior predictive sampling to, do model validation. So we get this. So RV's AZ has a whole bunch of really useful diagnostics. So what we're going to do now is check the quality of our model. So this was all model checking up here. But this is checking our MCMC algorithm. This is like, did the machine work? Did pymc-bart do what it was supposed to do, right? You can have really clean diagnostics and still have a crappy model. Crappy models can sample really well. Good models can sample poorly. So after you've established that if you're cool with this, now we can ask, is our model any good? And as I think I described earlier, posterior predictive checks is our main tool as Bayesians to do that. Just to repeat, so we've got a model that we fit with our data, and if this model's good, then if I simulate from this model as a data generating model, it should look like the data that we used to fit it. And so that's what this plot displays. The black line is the actual data, and the blue, there's a whole bunch of blue lines in there. That's the samples from the posterior predictive. The posterior predictive includes residual uncertainty about unknown parameters, and then it also includes stochastic variability, just normal error, stuff that had nothing to do with the model. That doesn't go away with more knowledge about the system, right? So there's noise, and then there's uncertainty, epistemic versus aleatoric, if that means anything to you. And you can see that the black line is well inside. If the black line was blue, you couldn't see it, right? So it's a pretty good fit. Doesn't mean it's a great model. It's a good fit. The mean is usually a good fit too, but that doesn't mean it's a good model. It's kind of the bias variance trade-off to a degree. Is it calibrated? Maybe not so much. So this is the delta of the empirical CDF. Ideally, you want what this is it's establishing coverage. So if I say that this is a 90% interval, is the true value really in there 90% of the time? And you really want it closer to this 0 line here. So it's kind of over. The claim is conservative in some areas and liberal in the others. So there's still work to be done here. It's not super well calibrated. Just means that you got to take the intervals with a grain of salt. Yes.
The delta of the, I believe that's the estimated CPF. Is that right?
Yes.
So ideally, you want that to be small. Is that correct?
0.
Yeah.
Yeah.
Zero, exactly.
Yeah. Yeah. It's directional. So over versus under coverage. Yeah.
And what about the orange part?
That's the actual data points, I think. Yeah. These are new. This is a new plot. It didn't exist like 2 weeks ago. So I'm still learning all this stuff myself. Yeah. RVs has no hesitation just to completely change things. But it's good because you get it, it's always better. It's just like didn't work the way it did last week. But that's progress for you. Yeah, and then sample. So here's where we predict out of sample. So now we're going to stick. So it's so easy just to, make predictions on new data, right? You just do set data, pass it X test, and see what we get. So this is the out of sample data set. And this is posterior predictive sampling. This is really fast. There's no more MCMC going on here. All it's doing is it's using the fitted parameters, sampling from those, pushing it through, and sampling from the likelihood sampling distribution. So this tends to go really fast. And coverage is not as good. Residuals, distribution, a little bit of a skew. So not too bad. And then I guess as you're used to with boosting trees and stuff like that, the kind of SHAP values that people use to kind of identify variable importance. Here we have partial dependency plots. So plot underscore PDB, PDP. And so for each variable, you see the effect of each variable on the output, So the partial influence, essentially, holding the others constant, right? So tire life isn't having a huge effect, but lap number is, stint is not, air temperature. So low air temperatures, but then it pans out, track temperature. So some of these are having a bigger effect than others. Venue has a huge effect, which we would expect. Venue, that is where the race is. I thought I had driver in here, but I guess I didn't. Cool. Do you want to get to, how much time have I got left? How much time? Plenty of time, okay. So another thing so how do you choose numbers of trees? This isn't terribly important. I don't think it's trial and error is one way of doing it. But what you can also do is model comparison. So what I skimmed over here was just adding a few more input variables and see whether it improves it or not. I'm going to skim past that. You can look over it yourself. It's just a slightly different model. I said before that you don't really have to do cross-validation with Bayesian models because you can actually approximate cross-validation using the MCMC samples. And this is a nice little trick. It's called PSYS-LU, and it Pareto-smoothed importance sampling, leave one out cross-validation. That's what it stands for. And so it mimics the effect of leave one out cross-validation. So usually what we'd have to do leave one out cross-validation here, right? You'd have to do MCMC sampling, which takes several minutes for each on this model. For each of a couple thousand values. So it would just take forever. But you can actually use information in the MCMC sample to approximate it. And that's what's happening here, which is great. There's no additional work to be done other than calculating a posterior likelihood. So one extra step, we do compute log likelihood. It used to do this on the fly automatically, but it only really gets used for model comparison. So we leave it as an extra step. And And so this is just 3 different models run with different values of m. And again, m is the number of trees. And what you get is a model selection parameter. So this is m equals 10, m equals 50, m equals 200. So the models do get better. Eventually, it may plateau where 200 and 300 are pretty close to one another. But then the important effect here, of course, is that sigma is shrinking towards some sort of floor as m gets larger. But 100 takes a lot, or 200, excuse me, takes a lot longer to sample than 10. I don't know if I have the number up here. Let's see. This one took a minute, about a minute and a half. That one took 5 seconds. So big differences. All right, last kind of 15 minutes, let me touch on classification. This is the other kind of general use, going back to CART models. And in Bayes, it's really easy. You really just have a different link function or a different likelihood to deal with stuff like counts or ordinal variables, things like that. So I'm going to compensate for using rat killing as one example by using happiness as the data set for this. We're predicting satisfaction with the people's lives. So this is the GSS survey in the United States. And so there's a variable called life now. So how happy are you with your life now as a function of a whole bunch of things, financial stuff, personal stuff, and so on. And so this notebook has 2 different treatments of this. One is just treating it as a binary variable, kind of a simpler, kind of like a logistic regression. Are you happy? Are you not? Of course, nobody's fully happy or fully unhappy, I suppose, but it's an easier starting place. And then an ordinal regression, where it's so the original data, it's one of these things you rate it, kind of like feedback forms for this tutorial, whether there's a 10 or a 1 or somewhere in between. So, and it's ordinal. You don't, the difference between 5 and 6 isn't necessarily the same as between 9 and 10. And so you can't, it's just this ordinal scale. So you can do what's called an ordered probit transformation in order to deal with that. And so it's very much the same as regression. We've got looks like 1600 or 1293 is the full data set. I'm fitting it to 25% here again just for speed. Let's see here. So we've got a design matrix. So we've got different inputs here. We've got inputs that are continuous or ordinal, so age, some sort of relative financial success, I think that is, whether you have a college degree or not, and then one-hot encoded things like gender and whether you're employed full-time, and then unordered categories like religion, race, ethnicity, that sort of thing. And so for binary output, it's really the same as in regression, except that, so same as before, we initialize BART with our split rules, number of trees, but of course, our output here is just going to be happy or unhappy. It's not going to be continuous, but BART is going to output a continuous scale. And so what you have to do is transform it the same way that we did with the rat poisoning example. We used inlogit before. This is inprobit. It's just another way of mapping probabilities onto real numbers. And then our likelihood is a Bernoulli. So a Bernoulli is just a binomial distribution with a sample size of 1. So it's a single coin flip. So you're either happy or you're not, and you only get 1 vote. You don't have to, if you asked the person 10 times, it would be a binomial distribution, right? Right, everything else is the same, and so you get kind of similar diagnostics. This one seemed to run, maybe, got the same warnings actually as before. And again, same problems actually. The R hat, there's a few R hats that are still not quite there. And ESS could be better, but well over the threshold value that we were looking for. And so this is just a comparison between BART and just a logistic regression. So an alternative to this would be to do a Bayesian logistic regression, main effects, which means there are no, I don't think there are any interactions here. So what BART gives you are interactions between, if you're financially happy and you have a full-time job, those are probably highly correlated. So they compare relatively well, slightly better for BART. But again, this is just first pass at the data. Does a reasonably good job. These are the top, the happiest people, but notice the red are unhappy people, so they were mispredicted. Where the y-axis here is the probability of being highly satisfied. And then this one here? This is our holdout reliability. So this is kind of how you check whether or not a logistic regression is calibrated. So it's putting them into the probabilities into bins. So it's continuous, but notice there's like one for each decile here. This one is pretty comparable. I mean, it's really who's closer to the red line for each of them, and BART is better up here. Logistic regression is better down here, I guess you would say. Right, and then so what this shows is essentially it's called cumulative inclusion frequency. So as you add, what we might want to know is, are all of these input variables necessary for getting a good prediction? And so what this is, it shows variables entering the model, starting with anxiety, and they're entered in corresponding to how often they are used as a splitting variable. So the ones that are used as splitting variables more tend to be more relevant. And so starting with anxiety, adding them in order until you get, so the dashed line is adding the full model with all of the predictors. And so after about 4 to 5 input variables, to the top 4 or 5, you're essentially getting similar performance to including all of the variables. Excuse me. Right, so this is a way of doing variable selection, essentially. And again, it's one of the things that doesn't show up very well on the screen, but there's a probability band right around here. So everything is probabilistic again. What else? I think we've got about 5 minutes left, so I think I'm going to stop there. One last thing I want to do before one last concept that I want to cover before I stop and answer questions is you can pass priors in, splitting priors in for the splitting rules. And by default, the priors are going to be uniform. But what you can do if you have prior information about the importance, the relative importance of different input variables, you can add additional weight to variables that you think should receive more attention. So you're essentially making the model do a little bit less work. So what we've done here, the split prior, all you have to do is pass it a set of essentially weights, and they get transformed into a probability distribution. So we call them inclusion frequencies. And so we're essentially going to specify things like financial quality of life variables over demographic variables. So we're giving demographic variables lower weight. We're giving things like FINRELA and full-time employment and those types of things higher weight. So we're giving them 10 times the weight. And these are kind of what happens. These are the inclusion frequencies under both of those priors. So you can see that you're getting higher inclusion for those variables. And you can do, again, model selection in order to try to choose the appropriate priors. You're not really biasing anything here. If you misspecify the prior, you're just making your model do a little bit more work. You can't hide from the data in that sense. I mean, you could do a really restrictive prior and say a weight of 0, and a weight of 0 means that they won't be chosen, essentially excluding them from the model. So this is a nice way of adding, because priors are all about constraining your model and adding either expert opinion or any kind of prior information that may have come from places outside of the data that you're currently using. So I'm at 5 minutes, probably 4 now. So let me stop there. The notebook's there for you to dig into a little bit more yourself if you'd like, and I'm happy to answer any questions.
Around the prediction?
The which, sorry? Oh, there you go, yeah. Speak.
Is there API to show how to quantify uncertainty around the prediction once you fit the bug model? How would you do that?
Oh, so that's what sample posterior predictive does. So it will make it doesn't make one predict. So when I run sample posterior predictive, by default it generates 1,000 draws from the posterior distribution, right? And so there's two things. There's the uncertainty around the parameter, which is the posterior, and that's what's in the MCMC sample. But then a prediction is adding sampling noise as well as the uncertainty. So when you make a prediction, it's a function of noise. It's also not noise, but stochasticity, as well as the uncertainty of the true value of the parameter. So you'll get 1,000 values for your prediction, and you'll have a distribution of predictions, and you can do a 90% credible interval on that, or whatever you need.
Okay, and how does this compare to other approaches such as quantile regressor from Statistical?
I mean, you can bootstrap intervals. So if you're doing a frequentist method, you do different subsets of the data and run the model 500 times, and you'll get an interval that kind of expresses uncertainty, but it's not a probability interval like this one is. One here and one here.
Well, first of all, thank you very much. Really interesting workshop. How does this, how does BART actually scale? So if I had to run this on a problem with 1 million rows, say samples, and maybe 100 features, how would this scale?
Not super well. So the MCMC is sort of data constrained in the sense that that's where the bottleneck is. Large models in terms of parameters typically sample quickly, but it doesn't scale well in terms of data size. The main constraint being that it is not gradient based. So that NUTS algorithm is very, very fast. Metropolis-based, Gibbs-based things can tend to be slow. There is a version, so there's an upcoming version of pymc-bart that will be in a upcoming release that is a Rust-based sampler. So they're going to squeeze as much out of taking things out of Python into Rust as we can. And then there's another algorithm that essentially smooths the trees and makes them continuous, which means you can take derivatives from them. You can use gradient-based methods. That's a relatively recent paper. That's not implemented yet. So at the moment, it doesn't scale really well to millions of rows. Just got to put them on a beefy machine. But it will get better over time.
Thank you.
We had a question over here.
BART, you find that there are more convergence issues because you're sampling from this horrible discrete spatial trees. And so like the usual tricks of, you know, more burn-in, higher target acceptance probability, do they tend to work, or are there other sort of issues?
Yeah, target acceptance rate is a good one. Yeah, there are a lot. The best way to fix convergence issues is almost always make your model better. And so that can sometimes be, well, in the case of BART, making sure that your data are well behaved, so you can transform variables, you can leave out variables that are causing problems or find a different proxy for them. It usually isn't, there are very few prior choices that you need to make here, and sometimes it's that, and you're not specifying any other model structure. Where I typically see that, so the nice thing about BART is that it's this latent process that you can actually just drop into a bigger model. So you can have a BART piece in your model. And I use this a lot when I worked in baseball, lots of sensor data that interact in various ways, and it's just a BART piece over here. And then there's a whole bunch of other model parameters that are estimated the normal way, and there's often an incongruence between the gradient, what the gradient-based methods are doing, and what the pg-bart sampler is doing, and they can interfere with each other sometimes. So I typically only see it when you have BART as a piece in a larger model, but it's usually the data's fault if it's causing a lot of those problems, and you have to look closely at your input data. And I think that's all the time we have, so thank you, everyone.